So now what we are going to do is take up a somewhat more complex example, right, and work through that as well, just to sort of get practice in the idea of how to implement folded architectures, right. One thing to keep in mind, in practice it is very unlikely that you will be manually doing this kind of folding. You are not going to individually decide what is going to go into each step. But the point of this course is for you to understand the principles involved. What does it mean to have different operations scheduled at different time steps, right? And when a tool or a compiler says that it is putting different operations in different time steps or different control steps, what is the implication? What does it mean? How is it going to do it? Okay? How does, if you were to do it by hand, how could you actually build such a system? That knowledge is the important part. Okay? So the larger example that we are going to take is something called a Biquad filter structure. Right? This is a somewhat common occurrence in signal processing. It is essentially a second order filter structure. It has both FIR and IIR portions, right, and it has a number of useful mathematical properties. Primarily from the point of view of the implementation, it turns out that this is a fairly robust and stable to a lot of different noise effects. Okay. So it's very popular in practice, it is used a lot. It turns, but as far as we are concerned, we are using it as a slightly more complex example of a signal processing system that needs to be implemented. So what I am going to draw is a data flow graph corresponding to one particular realization of this filter. We will look at all the different operations that need to be implemented. Then say if I have a finite set of resources, how do I go about folding everything onto this and getting it working. Okay. So the Biquad filter itself looks like this. Okay. So what you can see over here is there are 4 addition operations and 4 multiplications. Okay. The structure itself, overall you can sort of see what is happening out here, right. It has these 2 feedback loops, right, but the rest of it is essentially going in a feed forward manner. Right. So like I said, there are both FIR as well as IIR components to this structure, right. It is essentially a second order structure because up to y of n minus 2 and x of n minus 2 are being used in the computations that we have over here. Okay. Now later on we will actually see what the original structure looks like. This is already a structure that has been slightly retimed and pipelined to make it possible to do a scheduling. Right. The original structure actually looks a bit cleaner than this, but it does not matter. As far as we are concerned, we are just going to use this as our starting point. Okay. So what I am going to do now is to basically associate labels with each of these operations, but more importantly what I am going to do is define something called a folding set. Okay. In order to understand a folding set, it might be easier if we just go back to our original examples. What I am going to say over here is, if I do this, right, that is t of a1 equal to 0, t of a2 equal to 1, I can also equivalently write that by saying that there is a folding set which has the elements a1 and a2. This is the folding set for the adder. Okay. The meaning of this notation is basically that the adder has 2 phases in which it can operate, and because I have given this a1 comma a2, it means that a1 is going to execute in phase 0 and a2 is going to execute in phase 1. Okay. Even though I am using curly brackets, it is not unordered set. The order is important over here, a1 followed by a2. So in the next example, in this one over here, effectively what this corresponds to is the folding set is S equal to A1. What happens in the time instant 1? Nothing. So, I will just put a null over there, right, use the symbol phi to indicate a null element, and A2, right, either a null or just a dash, essentially to indicate that no operation is happening over there. Okay. And similarly for this third example, what I would have is this corresponds to S is equal to A2 at time 0, A1 at time 1 and nothing at time 2. And using the same notation, what I end up with is further, and before I give that notation, I am going to make the assumption that the adder is pipelined to depth 1, multiplier pipelined to depth, right, this is what we discussed yesterday. I am just repeating the same assumptions that we had yesterday. All that this means is, like I said yesterday, the multiplier, I can give it inputs on every clock cycle, but it has a latency of 2 cycles, so the output becomes ready only after 2 cycles. Another way of writing it is Pm is equal to 2 in this case, okay, in terms of the notation that we were talking about earlier, the Pm for the multiplier is equal to 2, okay. We will see how that applies when we are basically doing the DF computations. So, now with this information in place, I am going to write down S1, which is for the adder, right. I am going to assume I have one adder and one multiplier, right, and before I can write S, I also need to know what value of n to use. What's a suitable value of n? How many phases do I need? 4. Why 4? Because there are 4 adders. So, with one piece of hardware, I could do it in 4 clock cycles. How exactly, I do not know yet, but that is the bare minimum, that much I can be sure of. Similarly, 4 multiplication operations, I can finish those within 4 clock cycles, 4 phases. So, I will start off with the assumption that n is equal to 4. If it turns out that it is not going to work, I will probably have to change it and use a larger value of n. With that choice, n is equal to 4, what I have is, I have the ability to schedule 4 different units across 4 phases of time, okay. I am going to call the operations themselves as, I will just label all of them. This is A1, A2, A3, A4, M1, M2, M3, M4, okay. So, the set S1 for the adder, I am just going to give you this information, right, is basically going to be A2, A3, A1 and A4. In other words, another way of writing this would be to say that A1 is scheduled at time 2, A2 is scheduled at time 0, A3 is scheduled at time 1 and A4 is scheduled at time 3. Okay. So, both the notations that I have given here, where I put that bar and I put a number after it, as well as this set notation that I have, or the list notation that I have given over here, both are conveying the same information. Okay. S2, which is for the multiplier, M1, then M4, M2 and then M3, okay, which is equivalent to saying M1 happens at time 0, M2 happens at time 2, M3 happens at time 3 and M4 happens at time 1. Okay. How did I come up with this ordering? We will get to that later. Okay, that essentially is the problem. I mean, that ultimately is the most interesting problem in this entire thing, right? How do I come up with a valid set of these assignments so that none of the constraints are violated, and at the same time I am able to execute all my operations with a limited amount of hardware, in this case with one adder and one multiplier, right? So if I wanted to systematically take any data flow graph and implement it on a limited amount of hardware, effectively this is what needs to be done. I need to somehow come up with these assignments. How we come up with the assignments is the topic of scheduling. Okay, we will get to that next after we have completed this. The purpose of doing this exercise is to say, okay, once I have a schedule, how do I, at least this is one way by which I can implement it in hardware.